indeed, now we are, this is indeed, I think that this afternoon I will give also a short lecture about the residual stress measurement method, because Basil asked me to do that because it could be of interest. And indeed, apart this lecture about residual stress, indeed, this is the last subject related to shot peening. It is indeed, when I introduced the course, I put it in bracket because it's a very particular way to intend shot peening and unusual and not common in the end. Shot peening, while for metals, metal parts, shaft, crankshaft and rods and so on, it's usual shot peening. For polymers, is not so usual. Why? Because indeed, first of all, because fatigue is not a main issue for polymer, that the application of polymer are not most of time, at least for fatigue. And at the same time, the nature of the material is quite different, as we know. So, uh, so shot peening is not a usual treatment for polymers. Indeed, what are we doing? What I'm showing you now? Indeed, I will introduce some, indeed, almost all of the, I think, to my best knowledge at least, the paper that were published in the last, I don't know, 10 years, let's say, about shot peening for polymers. Okay, not by me, but by the other group in the world. And just to give you an indeed, this give you an idea of the few amount of research that has been done in this field. And at the same time, you will see that the application, the aim of applying shot peening and studying shot peening of polymer is not always the same. And sometimes it remains indeed, sometimes a bit strange remain anyway. And then I will conclude the presentation by introducing some results we have done recently that are indeed, our results are maybe more related to sandblasting, soft blasting, than to shot peening strictly said. And we will see an application where the aim is not fatigue, but to change the functionality of the surface, in particular to change, to improve, let's say, or to anyway, to influence, to modify the wettability of the material, the polymer material we have considered. And then some more about the simulation of soft blasting for polymers. And finally, I will conclude with an original application of shot peening for polymer for inducing a customized texture on the surface before concluding. Okay. This is the introduction. We have already said indeed about the application of shot peening for polymers. Indeed, the application in this study is quite limited, and sometimes indeed shot peening is confused with sandblasting. But also in this case, the systematic analysis study of sandblasting for polymers is quite limited, let's say. And let's see some of this paper I said about. I will scroll some of them. This is a paper. This is coming from Italy, indeed, from Bari. Was published less than 10 years ago. And what is the aim of this treatment? They are considering soft blasting. Okay, they are considering a polymer here. Okay, and what is the aim? They have considered different parameters for sandblasting, and we've needed. This is the, and they are using as the media are particles, and the material is sodium bicarbonate. That is to say, sodium bicarbonate that is used for soft blasting, let's say, is able to change and is soluble with water, and so it's used sometimes for this kind of finishes treatment, let's say. If you want to avoid any contamination, if you want to avoid that some particle remain on the surface and so on. In this case, they use this sodium bicarbonate to change the functionality of the surface. That is to say, to see if by means of sandblasting and by means of the particular surface morphology, let's say, induced by soft blasting, with this, on these fluorinated polymers with PVDF, we are able to obtain an hydrophobic or even super hydrophobic material. And what they say, indeed, they have changed the pressure of sandblasting or soft blasting from 6 to 8 bar, and the distance, the standoff distance was changed from 50 and 60 millimeter. Okay? And they measure by considering the different combination of parameters that they have tried, they were able to obtain, as you can see, super hydrophobic surface. That is to say that if a drop of water is put on the surface, the water is not spreading along the surface, but is remaining self-contained and with an angle with respect to the surface that is larger than 150 degrees. This is the super hydrophobic surface. And this is interesting because many treatments that are used for obtaining a similar result induce chemistry and chemical processes. In this way, this seems to be a quite simple process if we wish to obtain a surface behavior like this. Okay, another paper that has been published is this one. Here we are considering shot peening for polymer and for fatigue. Okay, and this is more similar to also the sample you see, the geometry is similar to the metal parts. Okay, but anyway, indeed, what this was an attempt to apply shot peening for improving the fatigue strength. And different peening parameters were used. In particular, the parameter that was used at this time was the time from 5 to 20 minutes in a wheel peening machine. Okay, and the result finally said that if you consider fatigue, the peening treatment is able to improve the number of cycles before failures. And the grade the treatment is able to do that is related to the peening parameter and the time. And so the best results were obtained with the yellow curve with longer treatment. Okay. This is another application, just to say, wettability, here is fatigue. Here what they are doing, here they are considering additive manufacturing, fuse filament and fabric process, okay, and they are using shot peening during printing. After 3-4 layers, they stop, they pin one layer, the blue one, and then they proceed. And in this way, okay, they are performing something like in situ treatment, and to discover if there is any mechanical enhancement improvement when the FFF is used together with shot peening as an hybrid manufacturing method. Okay, and how they have measured the improved mechanical property of the peened sample, the blue, by changing where the peening has been done. Here you see the hybrid sample by considering impact test. So we have a tower, we have an impact, an accelerator, and then we measure the energy and the deformation that is developed after the impact, and by means of the accelerometer we are able to characterize the nature of the impact. And what can we see here is that the different solution tested as printed, pinning on the surface of hybrid process is changing the peak acceleration and is reducing the peak acceleration by means of this hybrid process. Is good, is bad? Well, it depends on what we want to obtain and which is the application. For the application, they were interested in low velocity impact of this ABS process material, and then it's probably good. From a more general point of view, indeed, it depends. Okay, anyway, this is another, let's say, original application of shot peening. Okay, this is another paper about published in 2019, effect of shot peening and solidification on fatigue properties of epoxy-based composite material. So this is not a plain polymer, this is a composite material. And here shot peening is applied, is applied about fatigue. And how shot peening is performed? By using a wheel peeling machine. The diameter of the shot was the usual one, 45-50 Rockwell C. The diameter is around 2.25 millimeter, and the speed is around 40 meters per second. Okay, and for 2, 4, 5, and 8 minutes. So by changing the coverage, let's say. And the results are these. The shot peening is able to improve the fatigue strength for the treatment with 2, 4, and 6 minutes duration. After 6 minutes, indeed, the strength decrease. It means that we are in the overpinning case for this kind of material. And the same can be said for fatigue. So by means of by considering this paper, we consider that also for this kind of composite material, we are able to use shot peening for improving the fatigue strength, but at the same time, we should carefully manage the design of the treatment, the duration of the treatment, and otherwise, overpinning is possible. Here we are talking about laser shot peening for fatigue of a composite material. Okay? And the composite material was, the matrix was unsaturated polyester resin, and the powder, the reinforcement was aluminum powder. And laser shot peening is able to, also in this case for the material, it was able to improve the fatigue strength of around one quarter, 25%, with when the volume fraction of fiber is 7.5%. Okay, also the ultimate tensile test of composite was improved, and the author also said that laser peening is not recommended for low volumetric fraction, that is 2.5 and 5%. Okay, this is why they say that the laser shock waves are inducing a damage that is contained, let's say, by increasing the number of aluminum reinforcement. Here is another paper about wettability. Okay, this is in peak material. With peak as a matrix. Okay, and what is the conclusion? Going faster, the conclusion, let's say, indeed. By changing the blasting treatment for 5 to 30 seconds, the grid size was also changed. The roughness that resulting was, let's say, the variation of the rust show that the blasting time is proportional to the resulting roughness, no matter which is the peak that we are using. The bigger the roughness value, and the final conclusion is a bit weak. Let's say they say that the change of surface is inducing an impact on the hydrophobicity of the sample uh, without mentioning the wettability angle. Here we are talking about fatigue of composite fiber reinforcement polymer with, in form of laminate, and shot peening is improving the fatigue strength of this material, CFRP materials, and it's the fatigue strength of this this composite material is increased by shot peening up to 65%. And with shot peening even more, for 10 to 20%. So by means of the fiber, we are able to improve the fatigue and endurance by 50%, and shot peening is able to further induce another increment. It's confirmed that shot peening is able to improve the fatigue strength of composite material. Here, what can we see? Here is another paper, effect of process parameter and shot peening on mechanical behavior of ABS part. F, the diffuse filament fabrication. Static strength, okay, and they are shot peen this ABS sample fabrication, okay, and the effect of shot peening in this case is to reduce the UTS, but to increase the ductility, increase the elongation and the plastic deformation of the material. This is good for the application they tested, because this was good for making more efficient the peening done performed by using the damaged part, sharp or fractured bed, and not circular one, produce micro cracks, and this is not wanted. So overpinning remain. What's happening? Okay. This other paper refers to the effect of process peening on tensile test on polymer, that other process, that is image projection stereolithography. Okay. They have considered pressure of around 6 bar specified in the paper. In it, finally, we can conclude that we reported in the paper that is not strongly affected the UTS. And sometime is going to, even if not in a very, to reduce the UTS. It means that, conclude the authors, that microcracks that are affecting in a negative sample, the change of the can improve the final result. the paper that you can find in lit one more, but anyway, I don't think that more can be added, not more than 5, 6 can be added. Okay, the amount is small of paper, of research, more or less. The other half is dedicated to application, that is impact strength, static strength, and also from this, able to see that also for polymer of the material, it's important to correctly the right parameter in terms of shots. So now let's proceed with the other part of the presentation. And now here I'm talking about some results we have got by our research. And in the field of polymer, we are not considering fatigue. But you can see here that we are considering some other aspects. Let me summarize the test you can do for testing the wettability of, in general, and in this case of polymer, let's say. Here, indeed, how can we measure the grade of wettability of a surface? By considering a drop of water, control with a dedicated equipment, let's say, and by considering the way it appears once in stable condition. So we have the liquid, we have the solid, the vapor, and indeed the final result is something like this. Something that is a part of a sphere, let's say. And by measuring the angle here called as theta, that is a function of many different variables, we can conclude that the surface is hydrophilic, superhydrophilic, or hydrophobic, or even superhydrophobic. What is hydrophilic? Hydrophilic means that theta is less than 90 degrees. So the drops tend to spread. And if the angle is less than 50 degrees, we have a superhydrophilic surface. If theta is more than 90 degrees, we have an hydrophobic surface. That is to say that the drops tend to remain self-consistent, self-contained. If the angle, is even more than 150, okay, what does it mean? It means that we have a superhydrophobic surface. Okay, and the model that describe this behavior is called the Wenzel model and the Casey-Baxter model that describe this hydrophilicity, Wenzel model, and hydrophobicity, the Casey-Baxter, and depend on the condition of content and of the surface of the liquid and rough and the solid material, and in particular from the surface condition of the solid material, of the rough solid surface. And so what we have done, which experience have we done in this field? Here you see what we have done with the material we have considered: ABS, PTFE, PVDF, polycarbonate, and PVC. And these are the properties, the mechanical properties of this material, the tensile strength, and you can see that there is a range of this property from 30 to 50 for ABS and so on. PC is the most resistant one, that is up to 69 megapascal in terms of UTS. And then the Young modulus also in this case can have a range, and here is expressed in gigapascal. Fracture toughness is here, and yield stress is also reported. Okay, and what we do, the target material are the one that you see, and What are we using? We are using, considering what has been found by the paper that was published by the University of Bari some years ago, we consider also sodium bicarbonate. Why? Because this is non-hazardous, is low weight, is soluble in water, and so it's easy to clean if we need to clean the surface after the treatment, so even from rough surfaces, and it's possible to, by the data that is possible to find the state of the art, to get multi-scale roughness. Multi-scale roughness, that is what we want to get in to obtain for testing the wettability. Here is the experimental equipment that has been used. This is the sandblasting machine that we have used for the test. And we have considered this, we have designed and machined this tool that is a tool where the direction, the inclination is adjustable. So we can consider different impact direction on the material. Here is the sample is put and fixed here, and so we can consider also the angle of the direction of the inclination for the impact as a variable for assessing the result. The other result are the distance between the nozzle and the sample, the pressure of the media, the time, of course, and indeed, what does it mean? We have a number of parameters, and the full factorial plan was considered as more too expensive, time-consuming, let's say, and so we use a fractional factorial plan for developing the experiment. Okay. And this is a summary of what I have already said. A preliminary series of tests allow to define the final experimental plan. And this is indeed, you can see here the fractional factorial plan is anyway include a lot of experiment. Okay, this is the plan, and this is the factor we are considered. We have 5 different factors. The distance was considered 2 values, 50 or millimeter or 100 millimeter. The pressure is 2 or 6 bar. The time is 3 or 9 seconds, and 3 different angles were considered. Okay, that is the 0, 30 degree, and 60 degree. Okay. And here we have angle 1 and angle 2 that define the other direction of the tool where the sample is constrained. The roughness was measured by means of this pertometer, and the wettability was used by using a microscope, an optical microscope, and that it was tuned in such a way to obtain accurate value of this angle of the drop, let's say. Okay, what is this? Here we are talking about the characterization. We see the distance, the different factors, distance, time, and pressure. Okay. And here we see indeed what? The different color of the scale represent the different grade of coverage reached. The red color is where the more impact happens and so on. Okay, and you see here how the different parameter affects the way the coverage, let's say, that we were able to then to assess by means of an optical microscope. Let's see the result now. What can we see here? the material that were used, polycarbonate, PC, so PTFE, ABS, and PVDF. PVC was not considered because the wavelength was too high. Okay, and finally, indeed, in terms of roughness, indeed, the final result are here reported. And here we see the result that refer to the, for each single test that was done. Okay. Okay, so we start from this condition in terms of roughness, the different parameters, 6 parameters that define roughness, and starting from this condition, after each experiment, we find these other values. This is the modification induced by sandblasting according to the value of the parameter that were selected. This table is for polycarbonate. We have a similar one for ABS, of course. And then you can imagine how extensive was this experiment campaign. A lot of experiment, a lot of measurement of different material, different sample, and so on. This is for PTFE. Don't look at the number because it doesn't make any sense. Then we will make a synthesis. We will draw a synthesis of the final result. And these are, okay. And this is the same in terms of wettability. So in terms of wettability, we start from a contact angle that is this one. And we can notice that all the materials that we have considered are hydrophilic. Okay, they are hydrophilic because the angle is anyway is less than 90 degrees. Even PTFE that is 87 does not reach 90. The drop was arranged by means of this syringe, 5 millimeter each drop. And this is the test we did, okay, after for assessing the angle according to the different treatment condition that we have investigated. And the result are these, according to consider the material ABS, PVDF, and PTFE. These are the results before and after shot peening. And if we consider the situation before shot peening, it can be seen, can be observed that they are hydrophilic. That is to say, the angle is clearly visible, is less than 90 degrees. But if we are considering what's happened after some soft blasting, at least in this condition, we see that the behavior is quite different. The behavior is hydrophobic or could be also super hydrophobic because the angle is around 150, let's say. And okay, and here what can we see? Here is a more quantitative analysis of the result. We perform an ANOVA analysis for checking the role of the different parameters. And the result that of this analysis is that the behavior, the angle, so and the angle, wettability angle, is related to the surface roughness and morphology, of course. And we see here that in these two graphs, it is in the abscissa we have the soft blasting angle, that is the inclination, the direction of the cone of impact with respect of the normal of the sample, and then we have the roughness and the contact angle, and we see that we can obtain, especially if when the roughness is clear that it's different by changing the parameter, but also the contact angle, the water contact angle, is clearly influenced by the roughness itself. Reaching in as a maximum value 150 degrees, it means that you are in the field of the superhydrophobic surfaces. Here we see the difference in the appearance aspect of the surfaces after without the treatment. So the A row is without the treatment, no soft blasting. And then by changing the angle, the soft blasting angle, low, medium, and high contact angle, and we see that indeed the geometrical features that define the surface are rapidly changing with the angle of contact. Okay. Okay. How can we conclude? Indeed, by this study is confirmed that by means of soft blasting, it's possible to obtain super hydrophobic surfaces. Indeed, it's possible, first of all, to modify the wettability behavior of polymers and inducing a functionalized behavior. Indeed, also in this case, a more accurate study on the treatment itself must be done to completely assess the relation between the treatment parameters and the final behavior in terms of wettability. And indeed, it's not easy because you have seen that there is a huge number of parameters to consider, and the experiments are becoming more and more, even more and more. And so the number of experiments we should run is rapidly growing if you want to analyze all the parameters. From this point of view, also in this case, an approach that is based on the application of training for AI, that is artificial intelligence, could help in achieving good result, accurate result, by reducing the effort needed for the experiment. Okay, and that is to say that so far the complete dynamic, the fully understanding of of how this change of behavior has been obtained and how is related to the treatment parameter has not been defined, and the quantitative relation between the parameters of the treatment of some blasting and the surface itself must be found. Anyway, the result is good, is of interest. The application of a treatment like this at an industrial scale can reduce the environmental impact of the hydrophobic surfaces and can even reduce the final cost of the process we need for obtaining similar results, let's say. Okay, any question? You're not interested in polymers? Oh, please, there is a question there.
Sir, when compared to metals, polymers are having a different elastic behavior.
Yeah.
So when we actually apply this shot, I mean here, though we are going for soft blasting, still there is a tendency among the polymers to go for, rather than work hardening, their deformation might be happening more, right, sir?
Yeah.
In metal, preferably, we'll be having a work hardening kind of phenomenon happening. But in polymers, we might have a tendency for deformation when we apply the intensity and similar things.
You mean that we could have a more relevant effect of strain rate?
Yeah, I mean, in metal, if you are applying the short blasting, short peening, we can improve the residual stress and work
Yeah.
hardening phenomenon might be happening. But in polymers, since it is having a different elastic behavior, it might have a tendency to maybe come back to its polymer. Especially, it has got a tendency to regain its shape because of its elastic limit, and also if we apply intensity slightly higher, it might end up in damaging the polymers, right, sir?
Yes, indeed. The polymer are material with a completely different structure, indeed. So to think about the effect of shot peening as the same for metal is wrong. We don't have grains, we don't have a crystalline structure, at least for some polymers, and so on. This is the state of the art. Some experimental work without almost any theoretical background. What you say is true, and then they also some damage has been reported in literature. That is, if we exceed if the process parameters are too severe, we are immediately damaging the surface, much in a much easier way than with respect of metal. And this is due to the softer nature of the material.
So you actually cannot perform short peening on polymers. Rather, you can go for sandblasting on polymers.
You can perform shot peening, okay, but take care, but you must use soft parameters, of course. And this also, and also I don't know if you have noticed that in any of the paper I have shown, there is any residual stress measurement. They are not considered. Why? Because indeed the nature, the shot peen in the material is different, and also the residual stresses that will be generated will be not the same. We need something that is going to harden, no uniform plastic deformation to have and this is in the case of polymer, this is much less relevant, let's say.
Sir, what is the usual short material that is used in case of polymers?
For polymer, you are using hard material that could be ceramic, also glass, but also sometimes, as we have seen, also steel has been used. The hardness is around 45, not very hard. 45 Rockwell C is the hardness that is for this media.
The angle is changed to 45 to reduce the impact. Is that so?
We don't need very hard, indeed. The material is soft. We don't need very hard intensity, and we don't need very hard surfaces. Otherwise, the risk, we are increasing the risk that we are damaging the material.
Okay.
Okay. Indeed, and from a personal point of view, I'm not convinced that by applying shot peening to poly, we are obtaining a great improvement in fatigue. Okay, it has been proved that we can have, but anyway, not as as relevant as for metals. Shot peening or similar treatment can be exploited for this material more for other function of the surface, probably. Okay. Let's go now with the simulation of some. In parallel, we have done some simulation of the process. And what is in it? I will be fast. Maybe this is not very interesting for you, but anyway, why to perform simulation of sandblasting and why and which is the main difference of sandblasting with respect of shot peening simulation? The difference are the media. Shot peening, we can consider regular media, the same diameter or very similar diameter. The media are strictly controlled. As regards sandblasting, we have indeed we have a dimensional size range, let's say, but indeed the geometry is quite general, is randomic. We are talking about sand in the end. Okay, so this is randomic. And so what I'm showing now is how we have considered this problem and how we have developed the simulation of sandblasting with the good point we have got and also with the limit that I will highlight. And the material we have used is, we are considering in terms of target material is polycarbonate, PC. The media are considered to be in alumina, ceramics. And this is the model we have used for describing the behavior of the material, and here you recognize the Johnson-Cook equation that considers the strain effect, the strain rate effect, and the temperature effect. And the value of this Johnson-Cook law for polycarbonate were taken from literature, from this paper that we found in literature, where this equation for polycarbonate has been proposed and experimentally applied, let's say, with successfully applied. These are some scanning electron microscope image of the sand, of the media. We see here that indeed they are quite, the geometry is randomic. And so what have we done? We have considered different images. We have, in a manual way, we have assigned a number to each particle in this range. And finally, and then we have elaborated the image with this tool in black and white images. And finally, on the basis of the analysis of this image, we have schematized, let's say, the possible geometry in 4 different target geometry. That we are approximating the real case, and but according to what we have found by considering this image analysis, this is what we can do. So we have 4 different groups: spherical, ellipsoid, rectangular, triangular pyramid, that is this. And then we have each group we have 3 different sizes: small, medium, and big. And in total, we are able to simulate 12 different grains, 12 different media, sand media. Okay. What we can see here is some data about the shot velocity evaluation, okay, taken from this paper published on the Journal of Machine Tool and Manufacture. Okay, so you see here the dependence with respect of the nozzle position and the distance from the nozzle, and here is the particle velocity, also here, more in details. So this is the shot velocity equation. And as regard the finite element model, here you will recognize that the geometrical model we have already commented yesterday about the shot peening. That is to say that we have the target surface is a central part where the impacts are concentrated. At the end of the model, we have the infinite element to avoid the possible influence of the rebounding elastic waves. And so we have 2 impact directions to account in X and Z, and the horizontal direction. In total, we have 21 impact set. Okay. These are the resulting PEQ is the equivalent plastics deformation strain. This is by considering the different shots. Okay, here we are evaluating the step time evaluation. And this is the way a complete cycle is performed. Okay, and finally, if we want to reach the full coverage, we have to apply the classical Avrami equation that make possible to calculate how many impacts we need for considering 100% coverage. And this is what is done here. And a Python code has been developed to assessing these conditions. Okay. Here is which is the element that we are using. Indeed, the target surface was modeled by using reduced integration hexahedral element with 8 nodes. Also, the shot were considered as modeled with the same kind of element, so reduced integration, three-dimensional element with 8 nodes each. And here we see the superposition of the different media type that we have considered. This is the enlargement of the mesh, of the central part of the mesh. Here we can see the deformed shape of the target surface. And here you see the way we have filtered the point, following an approach that is similar to what we have used for, and we have commented yesterday, for additive manufacturing. So we have an original set of coordinates, then we have, using the filtering tool that we have developed, and finally we have smoothed data that respect the final the roughness parameters, but are avoiding any possible singularity induced by the numerical deformation, by numerical deformation. Here we can see the role of the surface morphology. This is experimental after the application of sandblasting 4 or 6 bar with different grade of magnification. And it's clear how the larger value of pressure is inducing more and more roughness and damage. Here is the effect of the standoff distance with the same value of pressure, 6 bar. And also in this case, it's possible to assess that if we are going farther, the indentation will be less evident. Okay, and now let's see the result. We have this result refers to polycarbonate, pressure is 6 bar, the standoff distance is 150 millimeters with 3-second impact time. Okay, and here we have what? The numerical simulation with, and comparison with the experimental one here. Okay, and we can see that the agreement we have found is satisfactory, let's say. In some cases closer, in some other cases is not so close. In some cases the scatter is more pronounced, and then, okay, but anyway the trend makes sense. The trend is the same, let's say. Okay. And I forgot to say that the experimental results that are reported in the graph are the average that we have taken by considering the measurement of roughness on three different samples. Okay, and this is indeed the same result in a table. These are the experimental one, and we see, to summarize, the result of set 1. So we have that the difference is between 10% and 20%, let's say. So we consider this result as satisfactory. there are other sets where other combination, other set of impact that were also considered, and the difference of RA in this case is the minimum one is something less than 8%. But anyway, whatever is whatever is the set that we are considering for impact, in the end, the trend is remained the same, between 10 and 20%. Okay, and finally, what can we say? Finally, we can say, indeed, I show you this analysis just to show you another way to simulate a process that is similar to shot peening, but from some point of view is even more complicated, especially due to the random distribution of the media. And we are obliged to group the media in categorized geometry, let's say, and then even if we have seen that even if we do this approximate step as an input step, and finally the result we can obtain and still can be useful for design, correctly designing the treatment itself. And so let's go now to the last part of the presentation, then I will close. Indeed, what I'm talking about now, I'm talking about a new way to apply no more sandblasting, shot peening, not for fatigue, not for improving the mechanical properties, but for changing the material, the surface texture. And the study was developed in cooperation with the Department of Design. That is to say that the final result can be exploited from a design point of view, and the application we will see in one of the slides of the presentation comes from a student that was a student in design, industrial design. Okay, okay, let's see what we are considering now. Indeed, we are talking about surface treatment. We are talking about shot peening. Now we know what the different shot we can use, cast steel, ceramic, or cut wire, and so on. And this is the machine that we can use for shot peening, but indeed I don't want to stay on this slide that you already know. Let's talk about surface patterning. This is an important field. Indeed, the surface is the interface we know between the environment and the solid material, and so also patterning play a role in the different behavior that the surface can have with respect of the environmental stimulation, let's say. And indeed, in the figure we see here, we recognize some micro patterning, let's say, that can be found in natural structure, snakes, shark, and so on, to obtain some particular property. And indeed, one of the most attractive field of research is today is the so-called bio-inspired design also for surfaces. So this study goes in this direction for surface patterning. And what have we done? We are talking about shot peening, and so we have defined a new type of media. No more a smooth sphere, like is done for usual shot peening, or ultrasonic shot peening, or what is, but the media that with a surface pattern, media that are obtained by using laser powder bed fusion or SLM, with a different pattern for each different possible shot. So we have the sphere, smooth sphere, the football. Why? Because it reminds somehow the ball that is used in soccer, multi-bump, golf ball, it reminds the golf ball, and the other one, lattice, icosahedron, and so on. Okay. The media were produced by using additive manufacturing. The diameter is around 8 centimeter. The small geometrical feature is less than 1 millimeter, is 0.1 millimeter. And the reason why we choose this geometry is by considering, and we've also the designer, they assess that the geometry could be able to produce an appealing surface. Okay, the material of the shot is it is still 316, and the target, we must have this requirement, and in the end we choose an ABS. First we model the problem. Again, the way we have modeled the problem is similar to what we have done in the previous study. So we have the shot target material that is modeled with the same, in the same way we did for the other one. The Jones Cook hardening model has been used for the material. And then we have run, let's say, this analysis by varying the media and by varying the coverage. And here we have some result, okay, in terms of deformed shape for the smooth ball, for the multi-bump, and for the this is the football media. And indeed, even after visual observation, we can see that the aspect of the surface, the texture of the surface is different. So what does it mean? That even with this randomic treatment, such as peening, we are able to maintain different patterning, clearly different pattern, by means of by using different initial pattern on the balls, on the media. Okay, and this is not understood initially. So, if you consider a football media, the final surface pattern will be different with respect of a smooth sphere or a multi-pump sphere and so on. And so by playing with this different media, we can also think to obtain different surfaces that can be used both from a functional point of view or even just for aesthetical application. Here is some result with an impact speed of 10 meter per second by considering the different media. This is the roughness parameter, areal roughness parameter, SA, SQ, and Z, and the other one. This is the same at impact velocity is 5 millimeter per second. And here we have SA and SQ for some of the shots. And then we have also performed some experimental test to compare with the simulation and then to draw some conclusion. We use, let's say, a very basic equipment, that is to say, an elastic, by stretching an elastic rubber, and then by considering the accumulated potential energy, we have estimated the velocity, and then attached to the back plate, there is the polymer plate where the indentation are done. That we have used and that were manufactured by additive. Some experimentally, these are, let's say, and then, okay, we see solution of the surface with the, and that follows indeed from a quite well what is also the numerical trend. Okay, and then we perform the same experiment also by media before shot peening. Influence of the initial roughness of the topical or even less at the nano for the modification of the surface, controlling the roughness of the media to control the level at different scale of the roughness of the surface. And here are some results in terms of the not polished media, and the difference is also observed. This image is not from a quality, of course. As a result, both numerical and experimental, and we see that in the end, okay, in all the cases examined, very fine cloth, but anyway, we can use the simulation to reduce the number of experiments to be done. And so simulation can be a good tool. So reducing the number, the number of experiments to be done. And finally, obtain this, the study is not finished yet today, but that are quite different than one. So by means of media, we obtain customized surfaces, and each of them can be compared, let's say, with another natural surface. This is the golf ball that is using a multi-jump mean other natural feature, let's say. Qualitative point of view at this stage. And what has been done, the student that followed, the design student that followed this is use this new shot peening treatment to design an object that is quite, that every one of us has on the desk, that is the cover for a cell phone. This is a application for the, but anyway, indeed, the rotation of this kind of shot peening for obtaining could be quite large. We can use different material for obtaining quite different surface that can be used for in daily life in the end. Indeed, when we talk with this study to, there was a colleague from, he had the idea this to the injection molding, because he said that if we are able to imprint on this part on injection molding, this could be because you have custom surface without, in the end, without any other treatment. And it could be a way to produce personalized custom in the okay, this is just for conclude the talk and time for lunch. I respect the deadline. 20:35, 5 late. Thank you. Thank you for your passion.